Module 2, Induction and Synchronous Machines, Hysteresis, and Drives. Section 1, Induction Machines. Induction machines are the workhorses of industry, used widely for motors due to their robustness and simplicity. 1.1 Open circuit test. Similar to transformers, an induction machine's open circuit or no-load test involves running the machine at rated voltage without load. Input power, voltage, current, and frequency are recorded. This provides data about core losses and frictional losses. 1.2 Short circuit test. Also called the blocked rotor test. The rotor is locked to prevent rotation. A reduced voltage is applied to the stator until rated current flows. This gives information about copper losses and leakage reactances. 1.3 Load test. During load test, the machine is connected to a mechanical load. Torque, speed, current, input power, and output power are measured. From this, efficiency and torque speed characteristics are plotted. 1.4 Circuit parameter and efficiency measurements. Using data from no-load and blocked rotor test, we can determine the equivalent circuit of the induction machine. With this, performance can be predicted under different loading conditions. Efficiency is determined by comparing input and output power. Section 4, Synchronous Machines. Synchronous machines are key components in power generation and grid operation. 4.1 Open circuit performance measurement. In the open circuit test, the machine is run at synchronous speed without load, and the terminal voltage is measured at different field currents. This provides the open circuit characteristic, showing the relationship between field excitation and generated voltage. 4.2 Short circuit test. With terminals short-circuited, field current is gradually increased, and short-circuit current is recorded. This provides the short circuit characteristic, useful for determining synchronous reactance. 4.3 Load test. Load tests involve connecting the machine to different loads and recording terminal voltage, current, and power factor. These results show how voltage regulation and efficiency vary with load. 4.4 Synchronization test. Synchronous machines must be properly synchronized before being connected to the power grid. Laboratory synchronization tests demonstrate how phase, frequency, and voltage are matched before closing the switch. Section 5, Hysteresis observations. Magnetic hysteresis is a fundamental property of ferromagnetic materials. By applying a cyclic magnetizing force and measuring flux density, a hysteresis loop is obtained. In the lab, hysteresis loops are observed using specialized setups. The loop illustrates energy losses due to magnetization reversal. This is crucial for understanding transformer and motor core losses. Section 6, Motor drive test with solid-state converters. In modern systems, solid-state converters are used to control motor speed and torque. In the laboratory, simple drive tests involve connecting motors to controlled rectifiers, inverters, or choppers. Students observe how voltage and frequency control affect motor performance. This bridges the gap between traditional machines and modern power electronics applications. Module 2 Summary. In this second module, we studied induction machines, synchronous machines, hysteresis observations, and motor drives. We covered practical test methods, performance measurements, and their real-world implications. Course conclusion. Throughout this course, you have learned how to conduct laboratory experiments on transformers, DC machines, induction machines, and synchronous machines. You have also studied hysteresis loops and motor drives with solid-state converters. These experiments help you connect theoretical knowledge with practical skills, preparing you for both academic examinations and industrial applications. Electrical machines remain at the heart of power engineering, and the laboratory is your training ground to master them.